Alright, sometimes our equations don't come to us in standard form, and then it's not easy to tell what A, B, and find C, and H and K and everything are, right? So sometimes we have to complete the square in order to put those in the standard form that we like them to be in, which means we want it to look like x minus h, just as a reminder. Squared over a squared plus y minus k squared over b squared equals 1. Okay, first thing we're going to do is position all terms containing variables on one side, grouping terms with the same variables together. Position the constant on the other side. We're going to complete the square. Sometimes that involves dividing out coefficients, which we are actually going to see on this problem. And then we're going to divide both sides of the equation by that constant, as long as it's not 0, so that we have 1 on the right side of our equation. And then we reduce to get our a squared and b squared numbers. Alright, so part of completing the square is also factoring those into perfect square binomials. Well, first we're turning them into perfect square trinomials, and then we're factoring them into binomials squared. That's what I'm trying to say. So x squared plus, oh, it's not a plus, I'm putting my x's together, minus 2x, and then I have 4y squared plus 24y, and I'm going to move my 33 to the other side. Now we can go through and complete the square. So x squared minus 2x, half of 2 is negative 1, and negative 1 squared is 1. So to complete the square on that, I'm adding 1. So what I add to one side, I have to add to the other side. Right? So then that part factors into x minus 1 squared, because the number I got when I halved the negative 2 was a negative 1, and negative 1 squared is 1. The next part's a little trickier. We need to factor out the 4, but not a y, even though you could factor out a y. You're not going to, because you're completing the square with that part. So we have y squared plus 6y. Let's go ahead and complete the square. So half of 6 would be 3, and 3 squared is 9. So we're adding 9 to get that perfect square trinomial. But in the overall problem, we're multiplying 4 times 9. So 4 times 9 is 36, so we're actually adding 36 to the left when we add that 9 in, which means we have to add in 36 to the right. Okay, so that gives us 4 times y plus 3 squared equals, combining this together, 4. And now we have this 4, we're on to step 3. We're going to divide everything by that 4. So divide by 4, divide by 4, divided by 4. The result is x minus 1 squared over 4, there's our a squared, plus, these reduce, y plus 3 squared. But instead of just leaving that like that, we're actually going to write it over 1, because that's our b squared. And then 4 divided by 4 equals 1, which is what we have to have on the right side. There, our equation is finished. Let's graph our center, which will be at 1, negative 3. So here, our a value is 2. Our b value is 1. So there. Sketch this in. And then we would find our foci by doing c is the square root of 4 minus 1. Which would be the square root of 3. So our foci would be located at 1 plus that square root of 3 to the right, comma, everything's along this negative 3 line, and then 1 minus square root of 3 to the left. So that's how we would write those foci in exact form, even though we got that weird square root answer. These are our exact values. It's actually easier to graph them if you know the decimals instead. But in this case, if we want our exact foci, that's more important than knowing exactly where they are on the graph with a decimal value. Decimal values are never exact, right? Just approximate. I'm just going to write foci again. We're doing our vertices because I skipped that for sake of time. I'm going to throw them in here. So our vertices ended up at 3, -3, because the square root of 4 was 2, and 2 plus that initial 1 value is 3. And then at -1, -3, because we take our center at 1 and we subtract the a value of 2. So that point is at -1. And I think I've done the whole thing. I hope that makes sense.